Good morning. My name is Daniel Sheehan. Welcome to the Friday morning plenary. It's a real pleasure this morning to introduce Dr. Henry Stapp from Lawrence Berkeley Labs and University of California, Berkeley, who will be speaking on quantum neuroscience and consciousness. Please give a hand to Henry.
My talk today will be on the topic of the significance of the work of Walter Freeman and Giuseppe Vitiello on the problem of the connection of mind to brain. As you all know, Walter was expected to be here today, but died on the eve of the conference and will no longer be here. I had, however, the good fortune to have a long series of one-to-one conversations with Walter for over a period of 4 months in Berkeley. And my talk today will be based on what I learned from Walter directly, confirmed by some recent meetings I've had with Vitiello. I'm going to begin by a very brief review of the present status of the situation in the mind-brain connection, and begin with a mention of the fact that great interest in this problem was stimulated by David Chalmers defining this as the hard problem, and the hard problem of the connection between mind and brain. And as a consequence of probably partly this definition, there's been a large amount of interest in the problem and many different possible solutions. I should mention, however, that this problem, although Dave defined it as the hard problem just a few years ago, that problem was and has been the core problem in Western science and philosophy for over 2,000 years. Now, this hard problem is defined by Dave, has stimulated great interest in many different possible solutions, many of which have been announced today. There are probably 100 different proposed solutions to this problem. But amongst all of the details there, one thing stands out as, or three things stand out as primary ideas that need to be mentioned to give even a rough idea of what's going on here. And these are the ideas expressed by the words materialism, dualism, and idealism. Dualism is the idea that reality consists of two totally different kinds of things. Mind, which is your thoughts, ideas, and feelings, on the one hand, and on the other hand, material stuff, which is described by ascribing mathematical properties to space-time points. So we have these two totally different descriptions, and the problem with this idea, dating from Descartes, as you know, is that because these two parts of reality are so distinct, it seems very difficult, if not impossible, to understand a rational relationship between them. In order to get a rational relationship between two different things, you need something that is common to them, something that allows you to build some sort of relationship between them. And unfortunately, these two things are so different that it is difficult to make a rationally coherent understanding of how they could be connected. As a consequence of this dilemma, two polar opposite ideas are very prominent. One is the idea of materialism, and the other is the idea of idealism. Now, materialism is the idea not that all is matter. Nobody can deny the fact that conscious experiences exist. But the idea in materialism is even if they exist, they don't do anything. In other words, they have no effect on the physical behavior, that the physical behavior is totally controlled by the interaction of matter with matter and certain laws of nature which bring in only the matter, and so the mind has nothing to do. And that idea has been illustrated in an interesting way by the idea of zombies. Now, real zombies are things that exist in Haiti, but the zombies that are talked about in philosophy and science are sometimes called philosophical zombies. They exist somehow in the minds of philosophers. But the point is still the same. If you take one of us human beings and just snatch away all the consciousness, according to the ideas of materialism, since consciousness doesn't do anything, plays no role, you wouldn't affect its behavior in any way. So it would be behaving in exactly the same way that a conscious being is, and we wouldn't be able to tell the difference. And that leads up to what I think is I'm sure is the most memorable incident in this long series of conferences, Tucson conferences. In this event, Dave Chalmers appeared on stage with what appeared to be a electrical hairdryer. But he announced that it was a consciousness detector, that it could detect consciousness. And so from the stage, he started pointing at different people. And for example, he would point to Penrose maybe and say, yes, there's consciousness there. And then he'd point to Hammeroff and he'd say, yes, there's consciousness there. And then he pointed to two well-known materialists, Patricia Churchland and Daniel Dennett. And he pointed his pointer and said, nope, no consciousness there. And the same with the other materialists. And so I'm sure that nobody who was at that meeting will ever forget that. The audience was very amused. But it makes the point that these these zombies could very well, some of us could be zombies, and you'd never know the difference. And so enough with the general background. I want to now get down to brass tacks, which is the, if I can advance this slide. So mainstream neuroscience believes in basically the materialist worldview. And now, in more detail, it is based on what is called the neuron doctrine. The neuron doctrine says that when we are trying to understand the connection between mind and brain, we don't really need to say much about most of the brain, because it doesn't really play a primary role, that the primary role is the neurons. It's the neurons that have the connection to our conscious experiences, and the rest of the stuff is helping out in some way, but it's not really the important stuff. And so neuroscientists talk about the neural correlates of consciousness. They don't talk about the brain correlates of consciousness, which is really what they probably ought to do, since you don't really know for sure exactly what parts of the brain are doing the job. So in the, now this neuron doctrine plays a very important role, because once you've said that the part of the brain that's important is the neurons, then it is a fact that the behavior of neurons is well understood and described in terms of classical mechanics. You don't need quantum mechanics to describe or you don't seem to need it to describe the behavior of the neurons. And therefore, a neuroscientist can be quite justified in saying there's no need to deal with quantum mechanics. We know it's somehow true, and if we're dealing with little chemical processes, then we can use quantum mechanics. But overall, we're quite justified in using classical mechanics because, as far as the neurons are concerned, they work very well. So the upshot is that the neurons, the neuroscientists feel completely justified in using classical mechanics and not worrying, generally speaking, about the rest of the brain. Now, the big statement of what Vitiello and Walter Freeman have discovered is what might be called the neuropill doctrine. Not the neuron doctrine, but the neuropill doctrine. Because basically what they have discovered is that there is a mathematically describable connection between what's going on in the neuropill and the brain. Now, what's the neuropill? The neuropill is kind of the gray matter, or a large part of the gray matter. It has other kinds of cells, glial cells, and a lot of water. So it's the embedding substance that embeds a lot of these neurons. And the experiments well, what I first should say is that this neuropill is naturally described in terms of a field theory. The neuropill is spread out smoothly over the surface of the brain, and therefore it is naturally a smooth surface, and you can talk about the electrical properties, the currents and the fields as a function of where you are in this space. So field theories are the way to naturally describe the neuropill. And now, it is true that there are classical field theories. However, Vitiello and Freeman, and Vitiello probably principally, went into a very detailed analysis of what happens in the neuropill, which I just should describe presently, and determined that the rapidity and the strength of these processes that I'm about to describe are so rapid and so strong that just looking at the mathematics, you cannot explain these properties that I'm about to describe in classical terms. You need quantum mechanical terms. So I'll go back to that in a minute. And first I will talk about what they have discovered, actually. And what Walter basically discovered is that if you look at the properties of the neuropill, there is this rapid creation and annihilation of certain structural forms in the neuropill. They start at a certain point, spread out and cover a large part of the brain, and they're very strong. So the rapidity at which these things happen and the strength in which they happen, if you do the calculations that Vitiello has done, turn out to say you just cannot explain these rapid creation annihilations of these neuropill properties in using classical mechanics. And so you've got to have a quantum field theory. And once you go to quantum field and want to explain what you're seeing, and these rapid creation annihilation of these structural forms, well, let me backtrack one step and say they also show that these structural forms that are rapidly created and annihilated, and then a new one comes in and is created and annihilated. So these rapidly created and annihilated structural forms are correlated to the conscious experiences of the subjects that are being examined. So there is an empirical correlation between conscious experiences and these events that are appearing and disappearing rapidly. So there's an empirical now correlation between conscious experiences and these rapidly created and annihilated properties of the neuropill. And so this is very different. People can talk about the neural correlates of conscious experiences, but the neural structure consists of very small modifications of neurons throughout the brain in a very complex way, and you do not have this direct empirical way of mapping a conscious experience into the actual structures in the brain that are causing it down at the neuron level, at the level of the synapses. And so, you're empirically speaking, you're on very much more solid ground when you say that you should be speaking of the neuropill correlates of consciousness than the neuron correlates of consciousness. And so that's the huge change here in what seems to be the empirical evidence that you can bring to bear on this question of the connection between mind and brain. And so the empirical evidence favors what you might call, therefore, the neuropill doctrine. It's the neuropill. And now two important things about this. One is that the correlation seems to be not just to the physical stimulus. When the physical stimulus comes in, say as a smell or something comes in, the brain acts upon it, and you see a lot of activity that's just corresponding to the fact that you had a stimulus, a physical stimulus, and the physical stimulus caused the brain to behave in a certain way, and you're going to see the consequences when you study the brain of the actual mechanical consequences of the stimulus. Now, so the meaning of the stimulus is something quite different, and a meaning is what it means, how the person is going to react, and what its significance to the person in terms of his ongoing actions. And as people know, psychoanalysts or psychiatrists know that you can manipulate the meanings by presenting it early on to the subject in different contexts. And the same word can have different meaning if you properly condition the subject. And the amazing thing is that these correlates, these neuropill correlates, are connected not to the physical part, but to the meaning of the stimulus. And so this is a pretty important difference here. It really is emphasizing the fact that we're dealing here with something mental, the mental correlates of the conscious experiences, not just the physical, purely physical aspects. And I can't read my own writing here. And, so let me say a little bit more about these events. It turns out that the events, these events, can be understood within the context of quantum field theory as phase transitions from something called the liquid phase in the ground state to from a gaseous ground state to a liquid different phase. It's a transition from gaseous to liquid phase, And this transformation occurs in a growing cone. In other words, it starts, for example, at a point in the olfactory bulb, and then spreads out like a growing raindrop. It advances radially, and with the structure on the inside holding all this structure that we're talking about, and on the outside it's just pure gas. And by the way, my wife, when she found out that there was gas in the brain, has taken to pulling on her ear to let the gas out, so when she feels a little gaseous. And this idea that there's gas in there that's turning to liquid in this rapidly spreading cone that spreads out rapidly and covers a large part of the brain, starting at the sensory is the thing. It's the rapidity of this rapid expansion together with the strength of it, and now together with the fact that it's correlated to the meaning that says that we're dealing with here is, well, that's not, the fact that it is so fast and so strong makes it impossible to explain in terms of the ideas of classical mechanics. Now, when you go to quantum field theory, in quantum field theory, there is something called Bose-Einstein condensates. So a lot of the very strange properties of matter, such as superconductivity, superfluidity, and in fact, the particle structure of the standard model are all explained by making significant use of these Bose-Einstein condensates, a very strange sort of matter. And so it's interesting that this other strange property of matter, namely of somehow being connected to consciousness, is connected to this part of the quantum world that has these other weird properties, you might say. So we're left now then on the basis of this really empirical evidence and the fact that when you really try to describe the mathematics of the structure, the physical structure, you need to use quantum field theory. It brings you to a whole new conception of what you should be looking for, what you should be doing when you do quantum mechanics, and when you try to understand the nature of the connection between mind and matter. So it would be a revolutionary change in the whole structure of how neuroscience should operate when you go to this deep level of trying to understand the connection between mind and brain. Let's see. I guess. So I think that's basically what I have to say. It seems that if all this is correct, the neuroscientists have been on the wrong track when they try to talk about mind, and their need to use an entire different theoretical structure, and moreover, is a theoretical structure, however, that is directly correlated to experimental evidence that is indicating what is needed. So instead of kind of working in the dark, even if you don't necessarily as a neuroscientist want to study all these deep complexities of quantum field theory, the fact that you're dealing now with empirical evidence for this connection puts you on a different track, and hopefully a much more productive track, because so far the efforts to understand the connection between mind and matter, mind and brain within today's conventional mainstream neuroscience has not been progressing well. So my message is that this work of Freeman and Vitiello portends a radical change in the way neuroscience works insofar as you're interested in the connection between mind and brain. Thank you. And
Why don't you come on up? Questions, please?
Hi, Henry, I'm Stu Coffin. We haven't seen one another for a while. I'm stunned at what you're saying.
Let me say, my hearing device doesn't seem to be working very well, so if you could please speak very distinctly, I will be able to understand you, I hope.
Henry, I haven't seen you for a while. I'm Stuart Kaufman. We've met several times in Berkeley. I want to just say something. I'm stunned by what you're saying. I'll be talking tomorrow about recent evidence that proteins can be critical, namely have fractal wave functions. And when they have fractal wave functions, there's beginning grounds to think that they act like high-temperature superconducting materials, possibly with Bose-Einstein condensate-like properties and electronic conductance. Very, very new. So it's amazing to hear what you're talking about, because the substrate just could be quantum criticality. And I want to thank you, and I want to get the slides and whatever is written up that Vitello and Freeman have done. Is that available publicly for us?
I didn't get it, no.
Okay, so this seems more like a comment, I think, right? Okay.
Yeah.
So, yes. So, could we keep?
By the way, in case there are technical questions, it would probably be very good to have Vitiello up here helping me answer these questions. Is he in the audience today?
What up?
Could you please come up here and help me out?
Okay, on the left.
I'm Karen Shaner, I'm Georgetown University, and I've been working closely with Walter the last year. First of all, Henry, he wanted me to remind you how thrilled he is that you're part of the team now. And Giuseppe will explain some of this now that you're there, Giuseppe. You'll be sure to mention the Herald's Journal and how all of this will be explained, and that it's neurophil. You are really such a terrific addition. Thank you very much.
Is that a question?
No. Okay.
Hi, I'm Tatiana. I'm Russian transpersonal psychologist. I would ask a question. My question is connected to your first slide. What if the world is more complex than just to be materialistic or idealistic or dualistic? Did you think about that?
What was the question?
I mean, the more complex than we can think about it and put it in just one
Vitiello,
position.
Can you answer? I didn't.
Well, in some sense, I apologize to be here because Professor Stapp is so great. Maybe there is something more complex than division, is unification. And this is reached through dynamics. So maybe we have to go up and down that stairs. Materialism, dualism, idealism, going back and back through that. Because each one is a facet of which appears to our perception. We cannot deny that this is material, but we cannot deny that here in this room there is a big emotional wave, and this is something which, I don't know, we might define like idealism. So I think there, instead of watching at the division, we should try to unify and have a dynamical view. Yeah, but it's complicated indeed.
I don't seem to be able to understand any of these questions.
Thank you. I have been working with phase transitions and criticality in brain processes for about 10 years. My question is, to what extent does Walter Freeman's most recent work with Vitiello cast back to his very strong inclinations to talk about self-organized criticality, which was his main theme 10 years ago? Let me just qualify this. I have been able to show that self-organized criticality gives you a key to unifying all the understanding from the 19th century phenomenologists, David Chalmers, and more modern work by people like Tononi. So if it relates to self-organized criticality, this is of extreme interest to both myself and Stuart Kaufman, who spoke earlier, because it's all part of complexity theory.
You see, thank you very much for this question, comment. As usually happens when you start to do some work, you collect from many places and you express what you learned. So Walter Freeman, which unfortunately is not with us, he started much before self-organized criticality came out, but on the side of neuroscience, just studying such amplitude modulated patterns which he was measuring in the brain and which have been afterward seen in a very clear way in functional nuclear resonance methods, magnetic resonance methods. There are real phase transitions in the brain. The brain is continuously undergoing phase transitions, and this makes it so important for the living being. Is completely out of the equilibrium, and nevertheless we are able to have a very stable functional activity. I mean our brain. So there are strict connections. Criticality, for example, is crucially important, and we have in our mathematics. So in some sense, we use orthodox quantum field theory. Only the idea was to consider the brain as a system to be studied by using such techniques, which is not in the neutron doctrine, where the brain appears more or less like a Christmas tree, let me say in this way, where you have flashing neurons up and down without any systemic view.
Thank you, that's a lovely answer.
Okay, so I think we're out of time. We're moving on to the next speaker. Thanks again to Dr. Stapp. Our next speaker is Kelvin McQueen from the University of Tel Aviv, who will be taking a position this summer at Chapin University in California in a very powerful group there with Aronoff, Taloxin, Kafados, so quite a stellar group that he'll be joining. This morning, he will be discussing wave function collapse theories and consciousness. Please welcome Dr. McQueen.
Thank you. What I'd like to talk about is some research that I've been doing with David Chalmers on the hypothesis that consciousness causes the collapse of the wave function. So there are two questions that underlie this research. The first is, what is the place of consciousness in nature? This question roughly corresponds to the hard problem of consciousness. The second question is, what is the physical reality described by quantum mechanics? This question roughly corresponds to what is called the measurement problem, or what I'll be calling the problem of quantum reality. Now, when you're motivating the hypothesis that consciousness causes the collapse of the wave function, there's really two ways of doing it. The first is as an answer to the first question. The second is as an answer to the second question. In this talk, I'll be doing the latter. However, towards the end of the talk, I will come back to the first question. So here's how I'm going to structure the talk. I want to start by getting quite precise on what the problem of quantum reality amounts to. Once I've done that, I want to introduce a general class of solutions to this problem, which we call M-property theory. Once I've done that, I will then describe the consciousness causes collapse hypothesis as a specific instance of an M-property theory. Now, the reason for doing that is what I want to argue is that the consciousness causes collapse hypothesis can be made scientifically rigorous in the sense that it can be made mathematically well-defined and can yield definite experimental predictions. Not just predictions in principle, but predictions that we might be able to falsify or verify within the next few decades. And the way that I'm going to be doing that is by using the framework of M-property theory. Once I've done that, I'll then briefly discuss some implications for the philosophy of mind, and that's where I'll come back to the hard problem of consciousness. Okay, so the problem of quantum reality. Textbook quantum mechanics is a formulation of quantum mechanics that was more or less selected to be the formulation of quantum mechanics to be taught in university textbooks, hence the name. This formulation of quantum mechanics goes back to the seminal work of John von Neumann in the 1930s in his book Mathematical Foundations of Quantum Mechanics. Textbook quantum mechanics describes two laws of nature. Firstly, it describes a deterministic law. This is described by the Schrödinger equation. Secondly, it describes an indeterministic law, which it describes by the collapse postulate. Now, without going into any detail about what these equations amount to, a serious question arises. Insofar as these are the two fundamental laws of textbook quantum mechanics, the question arises, when does one apply and not the other? It cannot be the case that a physical system evolves deterministically and not deterministically at the same time. So when does a physical system evolve in accordance with one and not the other? Textbook quantum mechanics gives an answer to that question. What it says is that the Schrödinger equation applies to physical systems when those systems are not being measured. The collapse postulate, on the other hand, applies to physical systems when those systems are being measured. Now, when you isolate that aspect of textbook quantum mechanics, a problem immediately arises. And this is what's called the measurement problem. Measurement is not a good candidate fundamental physical process. So that's putting the problem in terms of measurement itself. You can also put the problem in terms of the notion of measurement. The notion of measurement is not well defined. It's vague, it's obscure, it looks like it's just been plucked out of ordinary language. And we don't want notions like that in the fundamental formulation of our physical theory. Okay, so I want to go a little bit deeper into what gives rise to this problem. And I'll do that by looking at a very simple example of quantum mechanics in practice. So here's a very simple example. What I'm imagining here is a particle, I'm going to call it particle P, and it starts out in a definite position. It starts out being located at position X. And then I'm imagining that given the forces and constraints on this particle, it evolves at a later time into a superposition of being here and being there, which I've just represented by H and T. Now, I'm going to go through this example as well as another example later with some diagrams. I'm also going to put the mathematical formalism beside it. If you're not familiar with the mathematical formalism of quantum mechanics, then you can just follow my drawings and my descriptions of them. Okay, so given the setup, the Schrödinger equation tells us that our particle is now in a superposition of two different positions, being here and being there. Now let's imagine that we want to measure the position of this particle. So imagine that we build a device for measuring the position of the particle. And let's imagine that the device works as follows. If the device finds a particle to be located here, then it will display an H on its screen, thereby telling us where the particle is. If instead the device finds the particle to be located there, then it will display a T on its screen. That's how we've designed this device. Okay, so the initial state of the particle device system is, as I've written here, the particle is in a superposition of being here and being there, and the device is ready to do a measurement. So this is the state of the system right before the device has interacted with the particle. Now, what does the Schrödinger equation tell us about what happens when the particle interacts with the device? Well, due to what's called the linearity of the Schrödinger equation, what it tells us is that the microscopic superposition of the particle gets magnified up into the device. This is kind of like the Schrödinger's cat paradox. So the Schrödinger equation tells us that after the interaction, the device enters into a superposition of displaying an H on its screen and displaying a T on its screen. And I've tried to draw that by an overlapping H and T, but I don't actually know how to draw a superposition. Okay, so that's what the Schrödinger equation tells us about this interaction. But this interaction is also a measurement. So at some point, we need to introduce the collapse postulate. So let's introduce the collapse postulate. And what we get is a collapse of the wave function. So here I've depicted the collapse as one in which the screen collapses to representing H and the particle collapses to being here. But it could have gone either way. This is an indeterministic process. In particular, the probability that we get a collapse to the here state is given by the absolute value squared of the coefficient alpha, and the probability of a collapse to the there state is given by the absolute value squared of the coefficient beta. That's called the Born rule. So that's a very simple example of quantum mechanics in practice. And you can sort of see where the measurement problem arises. Where exactly do we apply it in this kind of process? And why here? Why does this count as a measurement? And in general, what counts as a measurement? So I think there's a slightly deeper and slightly better way of formulating this problem, which I'll define using this example again. And this formulation goes back to an article called 3 Measurement Problems by Tim Maudlin. This way of stating the fundamental problem is given by the mutual inconsistency of 3 propositions. The first proposition is that a measurement always has a single definite outcome. So with the example that we just saw, we did the measurement and we got a definite outcome. We got the H on the screen. The particle was found to be here. The second proposition is that the wave function of a system specifies all of its physical properties. So here was the wave function of the initial state of the particle device system right before the device interacted with the particle. And the idea here is the wave function, the description of quantum mechanics, gives a complete physical description. Quantum mechanics does not give an incomplete physical description. The third proposition is that the wave function always evolves in accordance with the Schrödinger equation. And we saw what happens there. We get a state that contradicts the state that I've written under proposition 1. We get a state in which the device is in a superposition of representing the particle to be here and representing the particle to be there. So it seems that these 3 propositions cannot all be true at once. The first proposition appears to be motivated by our observations when we do measurements. The second 2 propositions are motivated by quantum mechanics itself. Now, what's useful about putting the problem in this way is that we can categorize all of the solutions that have been put forward to the measurement problem or the problem of quantum reality in terms of which proposition they reject. So let's just consider that briefly. To solve this problem, you might want to deny proposition 1, the proposition that a measurement always has a single definite outcome. So this is denied, for example, by the many worlds interpretation of quantum mechanics. On this view, the device enters into a superposition of displaying contradictory results, and it remains in that superposition. But just as the superposition of the particle got magnified up into the device, so too does that superposition get passed on to the observer, who looks at the screen. And the observer evolves into a superposition of seeing an H and seeing a T. And then the observer's environment splits, and you get a branching multiverse. You might instead deny proposition 2. You might deny that the wave function of a system specifies all of its physical properties. A large number of interpretations take that route: Bohmian mechanics, cubism, various retrocausal theories like the 2-state vector formalism, and so on and so forth. Now, I want to focus here on the possibility of denying proposition 3. denying the proposition that the wave function always evolves in accordance with the Schrödinger equation. Clearly, this proposition is denied by textbook quantum mechanics. So textbook quantum mechanics denies this proposition and says, at least when measurements occur, physical systems evolve in accordance with the collapse postulate. But this collapse postulate, as we saw, is not well defined. It's collapse on measurement, but what's measurement? So by trying to solve the problem of quantum reality by denying proposition 3, textbook quantum mechanics gives rise to a new problem, the measurement problem. So M-property theory is in the class of theories that tries to deny proposition 3. And there are a large number of theories that try to do this. Henry Stapp's theory, the theory of Stuart Hameroff and Roger Penrose, OR, the theory of Girardi, Ramini, and Weber, Philip Pearl's theory, and so on and so forth. Now, one point I want to make about this buffet of solutions is this. There's no real consensus on which of these is correct. And I feel like that's because this is a really deep and difficult problem. So I think we're not really in a context where we can say one of these is definitely true. We shouldn't really be, I think, believing that one of these is certainly true. Rather, I think we're in the context where we just have to develop various solutions to this problem, analyze them, try and get predictions out of them, and see how well that goes. And so this talk is in the spirit of that project. So I'm not going to try and convince you that you should believe the consciousness causes collapse hypothesis. My goal here is less ambitious. What I want to try and show is that the consciousness causes collapse hypothesis should be viewed as just as scientifically rigorous as all of these other options, which is, I think, already a fairly controversial claim to make. Okay, now let's consider M-property theory. At the fundamental basis of M-property theory is this. So here's its fundamental goal. M-property theory is trying to stay as close to von Neumann's textbook formulation as possible. And there's some reason for doing this. Textbook quantum mechanics, after all, was the formulation of quantum mechanics that was selected to teach quantum mechanics in university textbooks, at least in most cases. And it seems to be the formulation of quantum mechanics that was used to push quantum mechanics forward over the past century. And so the idea is, let's not give it up. Let's not give up on it too quickly. And so what we want to do here to start off with is we want to just bracket the measurement problem for one moment. We want to set the measurement problem aside just for one moment, and we want to ask, what does this theory say about reality? What's the ontology of this theory? Just to get clear on what this theory is saying. And I think as soon as you ask this question, you run into an ambiguity. It's a fairly abstract ambiguity, a fairly abstract distinction that I want to mention here, but hopefully it will become more concrete as we move on. The ambiguity is this. What does textbook quantum mechanics take as more fundamental? What is it exactly describing? Is it describing a distinctive class of objects, what it calls the measurement devices, which are distinctive in virtue of exemplifying a special kind of property that is responsible for collapse? Is that what the theory is describing? So that way of going is M-property theory, and I'll clarify that in more detail in a moment. But there's another way of going, which is viewing the textbook as saying that really what's fundamental here is a specific kind of relation between a device and a property it's measuring, a relation corresponding to measuring property P. And that's what's responsible for collapse. And I take it that's Henry Stapp's view. And so here, measuring property P corresponds to what he calls posing a question to nature. So just before I move on to M-property theory, it'll be worth just briefly considering Henry Stapp's theory. Okay, so here's how I understand Henry Stapp's theory. I think it's useful to understand Henry's theory in terms of what it adds to textbook quantum mechanics. So as I understand Henry's theory, we have the collapse postulate, what he calls process 3. We have the Schrödinger equation, what he calls process 2. So that's there in textbook quantum mechanics. And then we have two new processes. So we have this process corresponding to measuring some property P. And that's what he calls posing a question to nature, which is basically the process of asking, what is the position of this particle, for example? And the idea is, when you pose a question to nature like that, nature responds with a collapse. And that's what gives rise to the collapse of the wave function. So what does this process 1 consist in? Well, here's where Henry introduces process zero. And process zero is, and I quote, some process that is not described by quantum theory, but determines the process one free choice. Now, I think Henry's work on this is extremely interesting, and I really do recommend, anyone who's interested in this topic, I really recommend his book, The Mindful Universe, very clearly written description of this topic. And I certainly don't have any devastating objections to Henry's view, but I think there is just a slight limitation here when we consider process zero. We don't, I think, get any exact account of process zero, and I think this more or less follows from the claim that it cannot be described by quantum theory, this stipulation that process zero cannot be described by physics. If that's right, it doesn't look like we're going to get an exact account of process one. But if we don't have an exact account of process one, then it looks like we don't know exactly when and why process three occurs. That is, we don't know exactly when and why the collapse occurs. But then it looks like we're sort of put back with the measurement problem, or the problem of quantum reality. So that's by no means a devastating objection to the view. It's at most a slight limitation that may push us towards thinking about another way of taking the textbook quantum mechanics literally. So let's now consider this other way of going. So the basic idea behind M-property theory is we want to take this notion of measurement that crops up in textbook quantum mechanics, and we want to try and precisify it some way. That is, we want to precisify it as some precisely defined M-property of objects. Okay, so the reason for talking about an M-property is we're taking this idea of a measurement property from textbook quantum mechanics. Ultimately, we want to get rid of reliance of the notion of measurement, and so that's why we use the abbreviation M-property. And then we characterize M-properties in terms of this basic law which governs them. And so here's just the basic law governing M-properties to a first approximation. An M-property, unlike other properties, refuses superposition. When it's about to enter into a superposition, it responds probabilistically via the Born rule with collapse. Okay, so that's a fairly abstract description of what an M-property is, so I just want to consider this in a lot more detail. So first, just with this abstract description in front of us, I just want to start by asking the question, what are the possible candidates for an M-property? What properties in nature could actually play this role? And once I've asked that question, I'll go into a little bit more depth as to how to define this basic law more precisely. Candidates on possible M-properties. What are the possible range of M-properties? To answer this question, we need to consider what are some empirical constraints. And there's really two important empirical constraints. The first is that the M-property cannot be too common. So for example, particle position cannot be an M-property. And we know that because we know that particle position often superposes. For example, we can infer that when we see interference effects after doing a double slit experiment. There's another constraint that goes the other way. The M-property cannot be too rare. So the M-property must at least be in the vicinity of measurements. That's because measurements always have definite outcomes. The collapse happens always when there's a measurement. So M-properties must be instantiated in the vicinity of a measurement. Okay, so these are the two empirical constraints on the range of possible M-properties. And it seems like there might be a number of properties that fit these constraints. So clearly where we're heading is consciousness. It seems like consciousness might not be too common and might not be too rare, so it might fit these constraints. I'm also going to consider here, because I'll be thinking about consciousness in a moment in terms of integrated information theory, Tononi's phi. So phi in Tononi's integrated information theory is a measure of the amount of consciousness in a given system. And it's given by the amount of integrated information of that system. So perhaps Tononi's phi is an M-property in the sense that it cannot enter into superpositions and responds with collapse. A more sophisticated way of developing the proposal would be in terms of Tononi's maximally irreducible conceptual structure, but for the most part I'll keep things simple here and I'll be talking about phi. There are other possibilities as well. Perhaps certain configurational properties might be M-properties. Space-time curvature. So I take it the Penrose-Diosi model actually fits the M-property model. It's an example of an M-property theory. Because I take it in this model, space-time curvature cannot superpose. If you get a superposition of two different space-time curvatures, this is an unstable superposition and it responds with collapse. So in that theory, space-time curvature is a kind of M property. And there are plausibly many other possibilities. For all we know, the M property does exist and we haven't even discovered it yet. Okay, so now that we've considered some possible candidate M properties, let's now consider in more detail this basic law governing M properties. So as I roughly characterized it before, M properties refuse superposition and respond via the Born rule with collapse. Consequently, the M property will collapse everything it's entangled with. Okay, so I'll start by illustrating that with a simple example, and this example is meant to show you how close this theory stays to textbook quantum mechanics. So I just use the same example. We start off with our particle P again. It begins in a definite location, location X, and then given the forces and constraints that are on this particle, it evolves into a superposition of being located here and being located there. We then want to build a device that's going to measure the position of this particle. And so we have the same device again. It is designed in such a way that if it finds a particle located here, it will display H on its screen, and if it finds a particle located there, it will display T on its screen. But there's a further stipulation. We're going to assume that this device has an M property. Moreover, we're going to assume that this M property is correlated with the state of the screen. And it's correlated with the state of the screen as follows. If the screen is displaying ready, as it is here, then the device instantiates a particular value for the M property, just call it M0. If instead the screen displays H, then the device instantiates a different value of that same property, call it M1. If the screen instead displays T, then the device instantiates M2. Now, just to make this concrete, you can fill in with some candidate M property. So if you want to fill in with consciousness, if you like, you can think of M0 as being bored, M1 as being happy, M2 as being sad. Or you could fill it in with phi. So then it's just going to be a particular amount of integrated information in this system. But at this point, it doesn't matter too much. I'm not, at this point, assuming what the M property might be. Okay, so here we have written down the initial state of our particle device system. The particle's in a superposition of being here and there, and the device is ready to do the measurement and instantiates M0. Now, what does the Schrödinger equation tell us about what happens when the particle interacts with the measuring device? As before, the device enters into a superposition of displaying H and displaying T. But because of the way that the M property was correlated with the state of the screen, the M property also enters into a superposition, according to the Schrödinger equation. We get a superposition of M1 and M2. But given the basic law governing M properties refuse superposition and respond probabilistically with collapse. And everything collapses, the particle and the device. And this happens in accordance with the Born rule. The here state, which is also the M1 state, collapses with probability given by the absolute value squared of alpha, and the there state, which is also the M2 state, collapses with probability given by the absolute value squared of beta. So that's the basic idea. Still not quite precise yet. We need to get a bit more clear on this basic law governing M properties. So what are some further constraints on how we can more precisely define this? There's one very important constraint that comes from what's called the quantum Zeno effect. So here's a very important constraint. When I've been defining M properties, I've been defining them as refusing superposition. But what does that mean? What does it mean to refuse a superposition? How can we get more precise on that? One way of reading that is to say that M properties absolutely refuse superposition. They cannot enter into superposition at all. And that's going to come into conflict with the quantum Zeno effect. So roughly the quantum Zeno effect states that frequent quantum measurement makes it hard for measured properties to change. So how does that give rise to a problem? Well, the following statement basically follows from the Schrödinger equation. For any physical property P, If a system evolves from some initial value of that property, V1, to some other value of that same property, V2, then it must evolve through superpositions of V1 and V2. Moreover, it does this in such a way that all of the probability is initially associated with the initial value V1. In particular, the probability of the initial value V1 continuously decreases from 1. What that means is, at the very first moment of the superposition, the probability for what the collapse will favor goes to the initial state. The initial state gets all the probability. So at the first moment of superposition, if we immediately get a collapse, because we're thinking of M properties as absolutely refusing superposition, if we immediately get a collapse, then the Born rule is going to put the state back into its initial state. But that means the system won't be able to evolve. So if you take the M property to be consciousness, the consequence is going to be that consciousness cannot evolve. It's going to be stuck. And that's a pretty bad consequence. And what I think is interesting about this is that it shows that the most straightforward way of formulating the consciousness causes collapse hypothesis yields a theory that cannot possibly be true. So should we give up on the consciousness causes collapse hypothesis? Well, I think not. I think we should instead take the quantum Zeno effect as a kind of guide for making the basic law governing M properties more precise. In particular, we should define the basic law of M properties in such a way that superpositions are merely unstable. And there's going to be a bunch of different ways of fleshing that idea out. So let me just consider a couple. So it might be that M property superpositions are more likely to collapse as the superposition components reach a difference threshold. Now, that's more or less modeled on the Penrose-Diossi model. So in the Penrose-Diossi model, if the M property is space-time curvature, then the threshold is curvature difference between the components. So if the curvature gets too different in the space-time, in the components of the superposition, that's when you get a collapse. And you can do the same sort of thing here. If the M property is consciousness, then the threshold might be something like distance into Noni's qualia space. That's one way of going. Another way of going is to say that the M property superpositions are more likely to collapse as the system has more of the M property. And this is an idea that's been explored very recently by Kobe Kremenizer and Andre Ranchin. So they're also using phi here. And on that view, the more phi that a system possesses, the higher the probability that its particles collapse to definite positions. Now, I think to decide between these views, we need to perform very precise experiments, and I'll come back to experiments in just a moment. Okay, now we consider the consciousness causes collapse hypothesis. So this hypothesis, I think, was first put forward or first advocated by London and Bauer in a textbook in the late 30s. I don't think von Neumann actually believed this theory. And I think it was first explicitly argued for by Eugene Wigner. But it was never really developed rigorously, and consequently, most physicists have completely dismissed this idea. And I think for good reason. There wasn't really any clear account of collapse given, and no clear definition of consciousness. But we can now solve those problems. So we can give a clear account of collapse using the M property framework, and to give a clear definition, we can solve the problem of there being no clear definition of consciousness as follows. We don't actually need to define consciousness. All we need is an account of the physical correlates of consciousness in order to make this theory precise. So if we take, again, the integrated information theory of consciousness as our candidate theory for the physical correlates, then we've got this phi, which measures the amount of consciousness of a system in terms of the amount of integrated information in the system. And that basically makes this theory precise as follows. If consciousness supervenes on its physical correlates, then consequently, if consciousness superpositions are unstable, then so are superpositions of its physical correlates. And so we can do everything in terms of phi superpositions. We can say that phi superpositions are unstable. And that means that all of this experimental research that's been done on collapse theories like the Penrose theory, like the GRW and Pearl theory, can just be passed over to this theory. And here's how that works. Those experimental procedures, diffraction experiments and so forth, are done on larger and larger systems in order to verify or falsify those theories. Here, we instead perform those same experiments, not on larger and larger systems, but on systems that have more and more phi. So perhaps by doing diffraction experiments, not with larger and larger systems like buckyballs, but instead with systems with higher amounts of phi, perhaps nanocomputers that we can program with large amounts of phi. Okay, I'll very briefly conclude with some implications for the philosophy of mind. So there's two ways of understanding this theory. The first is as a physicalist interpretation. On this idea, consciousness is nothing but integrated information, and fundamentally integrated information causes collapse. On the second idea, in the second interpretation, we've got an interactionist dualist interpretation. So on this way of viewing the theory, integrated information is just a correlate of consciousness, and consciousness is irreducible. Fundamentally, phi, or integrated information, is what causes collapse, and integrated information causes consciousness, and consciousness in turn causes collapse. And so we can just finish by considering whether or not either of these interpretations could solve the hard problem of consciousness. I think for the physicalist interpretation, probably not, for the same reason that integrated information theory doesn't solve the hard problem of consciousness. Why would consciousness be associated with integrated information? It doesn't seem like endowing integrated information with this new causal power, collapsing wave function, really helps. What about the interactionist interpretation? It seems like we might get a solution to the hard problem of consciousness here. So why is integrated information associated with consciousness? Well, that's because there are these new basic laws of nature which say, given that we've got certain states of integrated information, we've got certain conscious states. The traditional objection to interactionist dualism is that the mind-brain interaction is obscure, or we can't make it precise. But arguably, that problem is solved in the context of M-property theory, because we've also got these laws going from consciousness to the physics, where consciousness keeps phi in a definite state through the collapse of the wave function. And so the general idea that dualism somehow puts us outside of science or leaves us with an unrigorous theory, I think to some extent can be answered within this framework. Thank you.
Okay, in the interest of time, we'll take just a few questions.
Kelvin, very nice talk. Thank you very much. If you were to take M property as, rather than refusing superposition, as being superposition, and take the Penrose formulation of separated space-time geometry, then you solve everything. You don't need to worry about the quantum Zeno effect. And you could simply say that superposition, let's say in the brain, entangles with the observed superposition, reaches Penrose threshold for self-collapse, and you have a moment of consciousness. So you have your M property theory, except it's really a reformulated version of OR. Isn't that true?
Yeah, so I'm very sympathetic with OR theory. So as I said before, all I was trying to do here was put the consciousness causes collapse hypothesis on the same level of scientific respectability as OR and the other theories.
I wasn't aware we had any scientific respectability, but it's nice to hear you say that.
But I do have a few slight concerns, I guess, with OR. I don't think that they're devastating concerns, but they at least motivate me to explore alternatives. So it's not completely obvious to me that OR does solve the hard problem of consciousness. So we have these OR moments. We have these collapses in the theory that follow from quantum computations and microtubules. Now, why exactly should consciousness be associated with those kinds of collapses? It's not obvious to me that that question's been answered. And you briefly mentioned the issue of the quantum Zeno effect. I'm not sure if the quantum Zeno effect poses problems for Penrose's model, but it's not obvious to me that it doesn't. And it really depends on the nature of the collapse in Penrose's theory. If you look at the way that collapse is defined in dynamical collapse theories, you're left with tails of the wave function. That is, the collapses are not perfect. You're actually left, so in the case of Schrödinger's cat, you get a collapse in which you don't actually get a collapse to the alive cat. You're left with a superposition in which you get an alive cat with most of the amplitude and a dead cat with only a little bit. Now, I don't know if the same problem of tails is there for the Penrose model, but if it is, I worry that if the collapse doesn't completely collapse the superposition, then the threshold for collapse in your theory is going to be instantaneously met
as soon as you get one collapse. And that might bring on the quantum Zeno effect, but to be honest, I'm really not sure, because I'm not sure what exactly the post-collapse states in Penrose's model, which are done in terms of solutions to the Schrodinger-Newton equation, exactly look like.
He says no tails.
Next question, please.
Yes, so you briefly mentioned an alternative experiment where instead of doing double slit experiment with buckyballs, you would actually increase the phi of the system. So are you saying that the collapse would happen with the computer actually measuring through integrated information, or it wouldn't happen until a conscious human observer interacted with it?
Well, insofar as I was assuming that the integrated information theory describes the physical correlates of consciousness, then anything with a certain amount of phi, with a certain amount of integrated information, has consciousness. And so if we are to embrace the integrated information theory, then nanocomputers with sufficient amounts of integrated information are conscious. And that's why we can test the consciousness causes collapse theory using nanocomputers.
Okay, thank you.
One last question.
In the last chapter of von Neumann's book, he gave a proof that the cut going between, anyway, that the cut of where the measurement gets done, he gave a proof that the cut could be movable and placed in different places, in which this M theory has some flexibility. Could you comment on that? Or are you familiar with that proof?
Yes, I am. So I think in principle, so what I am assuming here is that in principle you can actually find an exact cut. So I think his proof, so how should I put this? So I don't think von Neumann actually proves that in principle the cut is always has a certain amount of room. In a collapse theory, so what I should say is that in the theory that I am assuming that there is a definite cut. So basically, the way that comes into this theory is where we assume that M properties are well defined. That's probably where the cut comes in. So as soon as we get the M property, that's where we get collapse starting to happen. And that would mean that the cut can't just be put anywhere.
Just one quick one. Quick one. Excuse me. One quick one.
Let's delay this until after the last talk, please. Thank you. Okay, for our final speaker in this session, we have Dr. Alyssa Ney, who is an associate professor at University of California, Davis, who will be discussing finding consciousness in the wave function.
So I want to thank Stuart for organizing this session. Really happy to be a part of this conference and for inviting me. I'm going to be talking about a particular interpretation of quantum mechanics called wave function realism. So I'm going to be addressing actually a different kind of question than was addressed in Kelvin's talk. And I want to spend just the first part of the talk distinguishing these different issues of interpretation in quantum mechanics. But let me just say a little bit about the broader structure of the talk. So I'm going to be defending, elaborating this view. The view is that, I don't know if I can believe this view, but I haven't seen any good arguments against it. So I've been working for the past several years trying to consider the arguments against the position. I can't see any good ones. So I think it's interesting and worth developing, because we do need some clear, coherent interpretations of quantum mechanics. But the view is that everything, the whole universe, including us, consciousness, everything, is grounded in the wave function, which is a field living on a very high-dimensional space. So I'll try to convince you what you should think are the good arguments for that. But the problem here that I've been working on, I guess most recently, is if you take that position, how do you recover the existence of ordinary macroscopic objects that seem that they have heights, widths, and depths? So they're three-dimensional objects. They're not objects that appear to be, at least, elements of a field in a very high dimensional space. And so thinking of how to address that question really forces us to revise our standard pictures of how microreduction works. So how do we view the relationship between macroscopic objects like tables, chairs, people, stars, and the kind of micro physical things that are supposed to make us up. And once we start to see that, we're going to have to revise our picture in general for how we see macroscopic objects as constituted out of the wave function. I think this opens up, if you are somebody who is a materialist, who likes to think that consciousness is something that's a feature of macroscopic systems, like objects that have brains that represent things, then that's going to open the door to a very different view about how consciousness relates to the microphysical stuff. So that's what I want to get to today. So I think I'll get to the slides on consciousness. I mean, I will get to it because I'm at a consciousness conference. But a lot of it is going to be just motivating so we can get very clear on what the picture is, what the interpretation is. So Kelvin talked about the measurement problem already, so maybe I don't have to say too much, but I'm going to do this anyway because I'm going to be using this, this example of this one quantum state. So we'll talk about this. So we're very familiar with Schrodinger's cat. This is just the example I'm going to use of an entangled state to keep things clear for the rest of the paper. You've got our cat in the box with this radioactive material. That has a non-zero chance of decaying before some time that I'm just calling T2. T2 is a time when we're going to open the box and see what happens. And if the decay occurs here, this stuff in the box, and that's going to release this lever, that'll release the hammer, that'll break the flask, and so on. And so we can describe this system in this way, by this quantum state, this wave function we'll call psi1, which has two terms, one term, this coefficient, and a term describing one possible state outcome for this radioactive material, that it doesn't decay, and then this term, which has got this ellipsis that's trying to describe the particle configuration that's involved when the radioactive material doesn't decay. So this includes, you have these particles configured in the form of a live cat, you've got a flask that's not broken, you've got a lever that wasn't released, and so on. And then we've got this other term that involves a decay term, and as well as everything that's going on in the other side. So dead cat, broken flask, pool of poisonous, okay, and so on. So we've got this entangled state. It's entangled because the state of the cat and the flask and so on is correlated with the kind of state of the radioactive material. So we've got these two terms. This is psi1. And so this is a way of representing what's going on before T2, before we open the box. Now, I want to get to this kind of first problem, the measurement problem, which is a problem that philosophers of quantum mechanics, physicists have been mainly concerned with for many years. The problem here starts just from noting this. We've got at T1 this quantum state, but the central dynamical law of quantum mechanics, Schrödinger equation, I'm just focusing on non-relativistic quantum mechanics in this talk. I'll say a little bit about extensions to relativistic frameworks later, but it's just going to be much easier to understand the view in the context of a non-relativistic theory. The central dynamical law of quantum mechanics, the Schrödinger equation, is deterministic. So if we've got psi1 that's the state of the system at this time T1, then there's a determinate fact about what the state is going to be at some later time T2. The trouble here is that the Schrödinger equation also constrains the system to evolve linearly. And what that means is just that if you've got initial state, psi1, the system's evolving according to this linear Schrödinger dynamics, then it's going to evolve, it will evolve to a state later that has this form. So you're going to have maybe a different coefficient here, but you're not going to see one of these terms dropping away. So it will never evolve into something like this. Now, the problem, this is what, okay, Kelvin was calling this something else, but this is the measurement problem, is that what the Schrödinger equation predicts is psi2. is that you're going to get something where C and these coefficients C and D, neither of which are equal to 0. But what it seems we know we observe is either no decay in a live cat or decay in a dead cat. We don't observe something, it doesn't seem like we observe something that's a superposition of a living and a dead cat. So that's the measurement problem. It's fundamentally the problem is that there's a disagreement between the central dynamical law of the theory and what we observe. And so there are many strategies, as Kelvin had on his slides, many strategies for reconciling this problem, resolving the conflict between what the theory predicts and what our observations are suggesting. The two kind of, I think, most popular options in some people who want to give a realist interpretation of quantum mechanics are the following. Option 1, you add another kind of dynamics to your theory. So you say that things don't always evolve in line with the Schrödinger equation. There are times when the Schrödinger dynamics do not apply. So you say it sometimes, in certain circumstances, or maybe spontaneously, systems collapse. And in my view, the most promising ways of doing this don't have the system collapsing completely onto a state that looks like this, where you have one term dropping away, but the more plausible kind of approaches to this have, such as a Gherardi, Rimini, and Weber formulation, or that of Philip Pearl, have a smoother collapse. So you're not going to see the left or the right-hand term dropping away, but either the coefficient C or D is going to come very, very close to 0. And so you've got this kind of smooth wave function collapse onto one or the other option. The second way, main strategy of reconciling theory with observation or solving the measurement problem is what Ever proposed, the many worlds view. And so here you say, look, if you're going to observe a system, what you're doing ultimately is interacting with it. And what that's going to result in is a new quantum state, we can call it psi3, where now you've interacted with the system, so now you have a state that involves also these terms for you seeing a live cat, you seeing a dead cat, and we as observers, other physical systems, are only ever going to be able to observe what Ever called relative states. So you're not going to observe the entire quantum state, you're going to observe a relative state, so this, or this. And so that's what's now called the many worlds interpretations, because we could think about two worlds here with two observers. The problem that I'm interested in is a problem that's completely orthogonal to this. So you can't really talk about the problem that I'm interested in without first understanding the measurement problem and kind of seeing, well, what are the solutions to this? Because we need to solve the measurement problem just to get a version of quantum mechanics that's consistent with our observations. But the question that I'm interested in is not what is a correct formulation of quantum mechanics. Do we need to add a collapse postulate? Do we not need to add a collapse postulate in order to reconcile the theory with observation? But once we recognize that whatever theory we have, whatever our theory is going to look like, we're going to have entangled states. What's the correct ontological interpretation of these entangled states? So what is a state like this? Sorry, that's the next slide. But what is an entangled state, like the kind of state that we see psi1 that describes a system before you open the box, tell us about the world? What's going on in the box in a state like that? Now, unfortunately, I don't think I need to talk about this so much in this audience, but there's been historically, unfortunately, a very influential view that we shouldn't be asking questions like this. In the interest of time, I don't want to talk so much or respond to this. I'll just say a couple of things to say why I think we should answer these questions. The first is, I think this view that comes from Heisenberg and Bohr, that we should only be looking at what's observable. We shouldn't be asking questions about states that, in principle, we're not going to be able to observe, is part of a kind of discredited philosophy that was influential around this time, that Heisenberg and Bohr were writing, the positivist philosophy, but that's been largely discredited in philosophy. And so as people who are interested in interpreting quantum mechanics, I think we should be working with the most current philosophy, which says we can certainly ask questions about things that are observable. There are facts there, and so even if we cannot know with certainty what's going on in situations that we can't observe, it's certainly coherent to be able to talk about those things. And the other thing I want to say about this is that I think in the early days of quantum mechanics, it might have been reasonable to think it just wasn't possible to give a clear, coherent metaphysical interpretation of what's going on in entangled states, because you thought that if you tried to do that, you would wind up with some kind of incoherent description of the world that was really wacky and didn't make any sense. But since at least 1952 and David Bohm's interpretation of quantum mechanics, we've seen it's possible to give a completely rigorous, clear, understandable description of what a quantum world is like. And so a lot of work in philosophy of quantum mechanics, work that's been done both by philosophers and physicists, has been trying to elaborate alternative, clear interpretations of what quantum mechanics is suggesting about the world and what these kinds of macroscopic objects are ultimately made up out of. Okay, so that's what I want to do here. So that's the state we're looking at. I want to start to get us into the wave function, to get to the argument for wave function realism. I just want to start with a kind of natural interpretation that you might start with here, that I'm ultimately going to say doesn't work. So what you might think here, if you're trying to say, okay, I've got the state psi 1, what is that suggesting about our world, is you might say, okay, well, what I have two terms here. Each is describing a kind of arrangement of particles. The particles in this box are arranged in a configuration where you've got this kind of radioactive material that hasn't decayed, you've got a live cat, you've got a flask, and blah, blah, blah. And there's another term that's suggesting that you've got another kind of particle configuration. So what you might try to do is say, okay, well, what's going on then at this time, T1, when we're looking in the box, is you've got these particles. So like we could focus on a particle in the tail of the cat and say, maybe this particle is not really something that has this determinate location. It's like a Newtonian particle, but instead it's a kind of field that's smeared out over these different locations. And so it's got some kind of amplitude that corresponds with this coefficient A up in the live tail part, and it's got this other kind of, it's got another amplitude corresponding with B, or B squared, in this other part. And we could look at all these kinds of particles in our system as smeared out, so that you've got this particle in the cat's head, and that's also kind of smeared out these two locations. So I think at first this is a kind of natural way to look at the kind of metaphysics of quantum states, is you've got these different kind of particle configurations. So this is this representation is a summary of a very complex particle configuration, and this is another one, and we can see these particles all as individual fields smeared out over these different locations. The trouble here is it isn't exactly right that oh geez, this thing. It isn't right that it's just that this, what I'm looking at, this blue particle is just smeared out over those two locations, and the pink one is smeared out over those two locations. Rather, what this state is telling us is the location of the one particle, which I have blue here, is correlated with the location of the other one. And so if you just look at this state as some kind of these fields that are smeared out over these different locations, you really miss the facts about entanglement, the facts about the correlations. And so the way to capture those facts, and this is why, this is how wave functions get represented, is to move to the kind of space that's very familiar from classical mechanics, from classical physics, since the 19th century, configuration space. So what configuration space does in classical mechanics, where in classical mechanics we're always assuming particles always have determinate locations, is it gives us a very simple way, a concise way of representing the locations of large number of particles. And so, for example, if you're dealing with a system of 10 particles, that's not that many, but if you're dealing with a system of 10 particles in three-dimensional space, the configuration space representation lets you represent all of the positions of all of those particles with one point in a higher dimensional space, in this case a 30-dimensional space. And in general, the dimensionality of the configuration space you need goes by the number of base dimensions you're working with. So here we're talking about three-dimensional space times the number of particles in the system. So if you want to understand or have a very simple way of capturing a configuration of n particles in three-dimensional space, and you need a 3n dimensional configuration space. And each point in that configuration space will represent the locations of all the particles. So in classical mechanics, configuration space is very useful. It's just a useful representation. When we move to quantum mechanics, what the wave function realist wants to argue is this is actually an indispensable kind of representation. The configuration space, unlike in classical physics, the configuration space representation isn't giving you any more information than the three-dimensional representation is. But in quantum mechanics, it is. And so we could see this just by considering again, this entangled state. So just to remind you, these particles, so those where we have these particles in the head and the tail. Okay. So you can look at this system in a three-dimensional representation. And again, if we consider an entangled state where you've got this one particle that seems like it's smeared over these two locations in three-dimensional space, and then another that's smeared over three-dimensional space, we can't really distinguish this from a quantum state in which the locations of the particles are independent of each other, in which that one particle, the blue particle, didn't have to be correlated in any interesting way with the state of the pink particle. When we move to a three-dimensional representation, or a 3n dimensional configuration space representation, we can capture this correlation in a way. So this is easier if I gave these locations suggestive names. When you look at things like this, you can see in the corresponding configuration space representation for the entangled state, this system is only able to be at these two places in the configuration space. The one I've suggestively labeled AC and BD, right? Because these are the locations that correspond to the first particle being at A and the second at C, and then the first at B and the second at D. But in the independent, where the states aren't correlated at all, you can see our system could be in any of those. And so what the wave function realist wants to suggest is that this is what we should think the world is fundamentally, because the fundamental picture of the world has to be the picture that gives us a complete characterization of all the possible states there are in the universe. And it's only in this higher dimensional representation that we can really capture the distinction between all the parts of state, all the different states there are. The three-dimensional representation is conflating distinct states, entangled and non-entangled states. Or I could have talked about different kinds of entangled states, where maybe A was correlated with D, okay. So this is the wave function realist picture. Our universe is fundamentally a field smeared out in a higher dimensional space that's like a configuration space. I say like a configuration space because it's not that this space is literally a space of particle configurations. On this picture, the particles are not fundamental. So the space has a structure like a configuration space, but it's not. And then this field, this is something that bothers some people because they say the wave function is a mathematical object. It represents states. It's not ontology. I didn't start calling this the wave function, but the wave function realist thinks the wave function is the thing that's represented by this mathematical object, this psi, and that is a field. That's the fundamental thing in our universe of which everything else is made up of. It's more fundamental than the particles. Now, this is the main argument for wave function realism, but I just want to mention, there's another one I'm just not going to have time to talk about. Another thing that's really nice about wave function realism is you don't have fundamental, what Einstein called spooky action at a distance. Because in the three-dimensional representation, you could have, you could say, well, the particles are in an entangled state, so if you see, see this particle at C, then that immediately, instantaneously makes it the case that you're going to find this one at A, not at B. And so from the three-dimensional perspective, that looks like you've got non-locality. You've got something instantaneously affecting something else that's far away. Come on. But in the 3n-dimensional interpretation, that's not what all you have in the fundamental picture here is just this one field evolving beautifully according to the Schrödinger dynamics. There's no action at a distance at all. So that's another nice thing. Now I have this slide because Janan Ishmael, who's a philosopher of physics at University of Arizona, wrote a really beautiful paper, this is on our website, called What Entanglement Might Be Telling Us, where she gives a really, I think, nice analogy with this wave function realist picture. And she makes this analogy with a kaleidoscope. So in the kaleidoscope, you see you've got all of these little beads in this, in the back side of the kaleidoscope, whatever that is called. And so, for example, we can focus on this one red bead that's in the kaleidoscope. In the kaleidoscope, what you have is one object, this red bead that's a three-dimensional object, that then in the image looks like it's many things separated, but in a lower dimensional space, a two-dimensional space. And so what Ishmael wants to say is, this is like the picture the wave function realist is giving to us. What look to be many things separated in a lower dimensional space is actually fundamentally really one thing in a much higher dimensional space. Okay, so this is really revising our picture, how we should think of what the fundamental reality is. It's not particles arranged in three-dimensional space. It's not even a field smeared out over three-dimensional space or four-dimensional space-time. What we have is a field in this much higher dimensional space. And what this goes along with, this revision in the microscopic ontology goes along with, as I mentioned in the beginning of the talk, is a revision in our accounts of microreduction. So how we understand ourselves and other macroscopic objects as built up out of this micro-ontology. Don't take a picture of this slide. This has this terrible typo. But, okay, so in the classical picture, and this is a kind of model of microreduction that philosophers of science worked with for, well, unfortunately, a lot of us are still working with this model. They think of the relationship of macroscopic objects to the micro-ontology as like the way bricks make up a house, right, by these mereological part-whole relations. But as we move to better understand the metaphysics of our more fundamental physical theories, we really need to revise that picture. And what I'm suggesting, I mentioned David Albert here. David Albert was the first one to really clearly articulate this view, this wave function realism, in a 1996 paper called Elementary Quantum Metaphysics. Once you accept this picture, we've got to really revise how we're looking at the way we're built up out of the micro-ontology, because it isn't like, okay, the wave function is a field spread out of space, but it's not like, in this part of the field, here's my hand, and in this part, here's my other hand. The different parts, as we saw already, each different point in the space corresponds to an entire particle configuration for the whole universe. So if anything, it's like all of us are in every point in the space. And so that's really going to have to change how we look at reduction. Now, I just want to mention there are challenges. There are clear challenges for this interpretation of quantum mechanics. So most recently, David Wallace and Chris Timpson and Wayne Meervold have raised a concern that this interpretation, in David Albert's work, has been developed in the context of non-relativistic quantum mechanics, and they want to suggest that it might not be so clear how to extend it to a relativistic framework. In particular, a concern is where particle number is not determinate, how do you understand the fundamental space that the wave function lives? This is something that I'm working on now. but we do need to address that. The other problem is, but it's not insurmountable. The other problem is the macro object problem. So this to me is a research program. This is a challenge for a philosopher to construct a plausible account of macro reduction or micro reduction here. But some philosophers of physics have raised this as an objection to the view that it's just simply not possible. If the world is fundamentally a wave function in a high-dimensional space, you just don't have any three-dimensional macro objects. And so what I want to talk about now is some of the responses that people have had. So probably the most well-known way of seeing macroscopic objects and three-dimensional objects more generally as arising from the wave function has been developed by David Albert, who is the main proponent of wave function realism. And he developed this most, I guess, in the most detail in his recent book, After Physics, that came out last year. And Albert's view there is a functionalist view. So what he wants to say basically is we should be functionalists. We already know we should be functionalists about macroscopic objects, and so we should be functionalists about three-dimensional objects more generally. So if you want to have three-dimensional objects, all you need is something in the more fundamental ontology that plays the causal role of three-dimensional objects. And so what he argues is the parts of the wave function are able to play the functional role of three-dimensional objects. There's no problem there. I've argued that there is a problem. It's not clear to me whether or not anything in this high-dimensional space that's like a configuration space is actually able to play the role of the functional role of three-dimensional objects. The way that Albert cashes this out at the functional role of three-dimensional objects is that the wave function needs to be approximately describable by a classical Hamiltonian that is terms for interactive distances. And the trouble that I have is that if the wave function is in this three n-dimensional space, not a three-dimensional space, there really are no such things as these three interactive distances. The problem is just that none of the many 3n dimensions of configuration space are the three dimensions of our ordinary experience. So you just don't have the interactive distances. The alternative that I favor is to try to recover macroscopic objects in two steps. So the first step involves getting the three-dimensionality out. So first you have to get out, okay, if you've got a wave function in this high-dimensional space, in what sense would it be true to say derivatively, not as a fundamental fact, but derivatively that there are three-dimensional objects, three-dimensional particles in that thing that may be configured in ways. And so the way that I suggested that we do this, which is more in line with the way that many philosophers of physics are thinking about space-time structurally, is to look at invariances between quantum states. If we can see the invariances between quantum states, and I think we can, as reflected in a three-dimensional representation as symmetries between different three-dimensional particle configurations, then we can see the three-dimensional description as tracking fundamental structure. I know this is too quick. On my last slide, I'll have references, and I have a paper, this in progress paper that I posted on Phil Papers that elaborates this in more detail. But once you get three-dimensional particle configurations out, then you can move from there to recover the macroscopic objects. And so, is this wrong? Okay. Then you can move from there to recover three-dimensional particle configuration. From the three-dimensional particle configurations, you can recover macro objects. And so roughly the idea is just that once you have all of these three-dimensional particle configurations, the wave function is going to have a different varying amplitude over these different regions of configuration space corresponding to these different particle configurations. And then we can say that each of these particle configurations is instantiated to various degrees. So if we think about the wave function as this field that's peaked at certain points, at each point you'll have a different particle configuration instantiated. And so ultimately what you're going to have is multiple me's, multiple you's, multiple chairs, multiple audiences, multiple mountains, and so on, all instantiated to varying degrees in the wave function. So finally, let me just talk about consciousness. So if you're drawn to an approach that ties consciousness to the process of wave function collapse, then you've already found consciousness in the wave function. So you don't need the rest of this. Once you've solved the measurement problem in a way using the collapse postulate, then you can find consciousness. But if instead you favor a view that takes consciousness as tied to the behavior of higher level systems, so maybe you think that consciousness is something that's tied to representations of a subject's own mental states or their environment, then you're going to be treating consciousness as a macroscopic phenomenon. And what I've just tried to argue is that wave function realism, if you take this to be a natural, promising interpretation of quantum mechanics, that's going to make you revise the way you take macroscopic reality in general to be constituted by the fundamental ontology. And so there are a couple, I think, interesting consequences, or possible interesting consequences here. So just as there exists multiple macroscopic objects instantiated to varying degrees in parts of the wave function, there are also going to be multiple representations instantiated to various degrees in these different parts of the wave function. And so the plausibility of wave function realism then seems to bring with it the possibility that there's more to our conscious experiences that we may be aware of. On the other hand, if you want to say, well, I'm skeptical of that, I have some kind of revelation thesis that I accept, I don't think that there are aspects of my conscious experience that are inaccessible from a first person's perspective, well then that's why I call this slide Finding the Wave Function in Consciousness, because then it looks like you'd be able to find evidence of these multiple representations in conscious experience. And the last thing I just want to say is these won't be, so from the perspective of the representations, which will be in three-dimensional representations. They will seem incompatible, but again, fundamentally, what the underlying metaphysics gives you is a completely consistent picture, a completely consistent underlying metaphysics that then has room for emergent or non-fundamental derivative incompatible possibilities for representation, or actualities actually for representation on this view. So thank you.
Okay, we're just going to take a few questions directly, and then we're going to invite Kelvin back up to field more general questions. So on the right, please.
Oh, well, I wanted to ask it to the whole group. So.
Hi. I have a question about the cat experiment, and it's something that I haven't heard some people talking about it. And if it was mentioned, I apologize for not paying attention. This problem of the measurement when the cat is alive or dead, I have a reference in 2015, the scientists got the Nobel Prize about measuring photons, and they claim that they have a methodology to observe both if the cat is alive and dead simultaneously when the photon is actually a wave and a particle. How would that change our views about quantum mechanics if you are able to observe both the state, the cat state, without, when you observe, you're not changing the quantum state of it. You are able to see both at the same time.
Are you talking about weak measurements, or?
This guy is called Brown et al. In 2015, and they got the Nobel Prize to observe a photon in both the state when it's a particle and a wave. How would that change our view if we can see the cat both dead and alive at the same time?
I mean, I think that's fine for wave function realism. I think that's going to be more of a problem for a view like a Bohmian view, or a view according to which you want to say the states, the locations of particles are always determinate. On this view, that's just not true. I mean, now this depends on how you want to solve the measurement problem. So, but I'm not sure exactly what, like what experiment you're talking about, but that's in principle not incompatible with the view that I'm proposing or defending.
Okay, thank you. Hello. There's a philosopher called David Pearce who proposes that consciousness is indeed sort of like a Schrodinger's cat state. He presented in a concurrent session about basically quantum coherence potentially being able to account for phenomenal binding or the combination problem in panpsychism.
At this conference?
Yes.
I'm sorry, I've had a fever for the past 3 days, and I haven't been able to go to as many things as I wanted to. If he's here, can he send me that maybe?
Yeah,
Thanks.
you can find it in physicalism.com.
Okay, thank you.
And so if you have like any idea, or like what is your opinion about how these can come into play with the combination or phenomenal binding problem?
Oh, yeah. So I wasn't trying to solve the hard problem or the binding problem, or I wasn't trying to solve any of that here. So, I mean, I'm a metaphysician, so what I'm trying to do here is better understand like frameworks that we can have for microphysical reduction. And now exactly how the account's going to go to solve these various aspects of easy or hard problems of consciousness, I'm not trying to give an account of that here. But I'm very interested to read that. Thank you.
Thank you.
Hi there. I'd like to make a statement to see if what I'm about ready to say is consistent.
Let's restrict
with your
this to
theory.
questions, please.
So the question will be, is this consistent with what I'm hearing your theory is? Okay. That the fundamental level is a wave level, and that the waves are differentiated in various energy states, frequencies, an array, geometries, holographic arrays, and that's the fundamental nature. And so therefore, whether it's a particle or whether it's a wave, whether it's entangled particle superposition, what's really happening is that each thing we think is a thing is really an array of waves. Is that consistent with what you're saying?
So the way you're describing it is each particle would be many waves, but it's
an array of waves.
An array of waves, but the picture is that fundamentally there's just one thing. So there's just one field or one wave, and everything is contained in that one thing. So it's more like a monism, where there's one thing.
One wave.
Yeah.
Okay. Thank you.
Sure.
Hi. Thanks so much. I just had a question about introspection. On that last slide you wrote, if you're skeptical that there could be aspects of experience that are inaccessible from first-person perspective, we might be able to find evidence of these multiple partially instantiated representations.
Yeah, what do you think about that?
Well, I was going to ask you to say more. I'm new to all this. I find it fascinating, but just having just heard that sentence, I couldn't really think of how that could go. How that introspective process could go. You should also talk to Andrew Lee, who had a talk on the deep structure of experience. But I don't have much of a dog in this fight, so I was just wondering if you could say more. It's also not a fight. That was the wrong metaphor. I don't really have a stake in this literature. Yeah.
So right. So this picture, the wave function realist picture, that's been that's been proposed by David Albert, has it be the case that the structure of the fundamental space is like the structure of a configuration space. So right there, it's going to be the case that at every point in the configuration space, in the fundamental wave function space, does correspond to an entire particle configuration. So that means that if the wave function is smeared out, which of course it's smeared out because we're not living in a classical world, it's going to be smeared out over different parts of this space, then there are going to be multiple particle configurations. And so then there will be multiple representations. And so if you think that experience is reducible to a matter of representation, then that means that there are going to be multiple experiences. So I don't know how, I don't know what that feels like, but that's, I mean, the proposal, well, sorry, I should say, the proposal would be that you do know, well, there are the two options. Either these aspects of our representations and experiences are hidden from us, so we don't know what it feels like, or if you think that, no, that can't be, that if it's part of your experience, then it's part of your representation, these kinds of representations, it's part of your experience, then you're aware of it, then you do know what it feels like. So then the answer is, it feels like this. This is what it feels like to have these multiple representations, right? So, yeah, that's all I can say.
Great, thanks.
So let's open things up to any questions for any of the speakers at this point.
So I think you actually answered your own question. Hi, I'm speaking. Okay, so I think you've actually answered your own question in a way. Dealing with representational spaces, the larger wave function, and multiple experiences. I think there's something that we're kind of missing in the wave function and the multi-world, the many worlds interpretation of quantum mechanics and all this stuff, where there should be many representations and where the difference between the classical and the quantum interpretations and the experience of it. Because at one level we're saying that there is this unified wave in this whole unity, but I think that what we're missing is that we are the multiple representations of the same, of all these superimposed possibilities, that we literally live in this superposition, that you and I and so many different I's, which we recognize often as, oh, there's like another me that's made another choice and gone into medicine instead of this field or that field. I think there are all of these I's superimposed, and that we are actually living in and affecting each other in this consciousness field of the quantum field of superposition. I think that the two are inherently superimposed, and that we're always in that field.
Yeah, let me just say one thing there, though. So in this picture, it's not just the many worlds. So if you accept the many worlds theory as your preferred solution to the measurement problem, then yes, then you will have, like, for example, in this case of the Schrodinger's cat, you'll have like the two bumps, right, in the wave function. And so you'll have the bump experiencing the live cat and then the bump experiencing the dead cat. But what this view is saying is, even if you don't have, so I'm not trying to disagree with anything you're saying. I just want to emphasize this because I didn't emphasize it in the presentation. I wanted to, but it's related. Even on a collapse approach, so even if you're not a many worlds person, and so you think one of the other bumps like kind of peters out or dies away, it's still going to be the case that you've got these. Since the wave is smeared out, you're still going to have these multiple representations. So that's why I wanted to distinguish the issue of the measurement problem from this issue of ontic interpretation.
It just doesn't feel to me logical. When you say the wave's smeared out, I don't think the wave is smeared out. I think we are living in the wave very clearly in this state of perpetual superposition of consciousness and classical phenomenal dynamics. I think the duality itself is a delusion. But that's okay. Thank you.
Hi, this is a question to Kelvin. So you suggested to make some kind of empirical test of this M property theory based on IIT in 10 years. But I think you can already test it already by now, just by first starting with, if the IIT is correct, then attaching any kind of very simple sensor, like photodiode or whatever, which can determine the position of the particle through the double slit experiment. I'm not sure how exactly you build it, but if that's attached to just single memory chip or something like that, then that will have a minimum amount of phi, which is just really, really minimal. And if you attach it with something more complicated, then phi gradually increases. And according to your hypothesis, I'm not so sure whether you predict that, as the phi gradually increases, the probability of the wave collapse actually increases like an exponential or something like that. And you can probably precisely measure that by increasing, really elementary near zero phi system, or something like eyes of the insects, which we probably expect to be very low phi but still non-zero. And you can also anesthetize the insects or something like that to really vary the phi, and then see how it changes this wave collapse probability function.
Yeah, great question. So there were really two ideas that I put forward, two different proposals for using integrated information theory to make the view precise. And I think it's not so easy to test either view on systems of low but non-zero integrated information. So on one of the proposals, the probability per unit time for collapse is a function of the integrated information of the system. So the more integrated information the system has, the higher the probability per unit time that the system will collapse to a definite state. Now, what that means is if you've got say, a nanocomputer or whatever, a system of just a low amount of phi, and you're sending it, say, if you're just doing like a diffraction experiment or something like that, it actually won't predict that you'll get no interference pattern. What you need to do is you need to increase the integrated information quite a lot in order to get the prediction of collapse. And I think that's going to be a lot harder to do, but I'm not sure. I mean, this is something I'd like to ask you about, because I know Scott Aronson has been thinking about ways of programming very simple systems so that they have a very large amount of phi. And that may be able to make the first proposal experimentally verifiable now. But on the other proposal, I wasn't actually using integrated information. On the other proposal, I was thinking more in terms of Tononi's idea of maximally irreducible conceptual structure. And so this would be the idea that a system is more probable to collapse if the components of the superposition exemplify a certain distance in qualia space. So that's a much more abstract idea, and it's not completely obvious to me that you can just use phi to test that theory. So I think it's not quite as easy as you suggest.
Question for Alyssa Ney, over here to your right. Hi. I'm wondering if it would be possible to present pretty much the identical argument you gave us in a sort of neuroscientific context, because you were talking about the wave function as a point in a higher dimensional configuration space and argued how you could reconcile that with objective dead and live cats or chairs and tables. But could you also talk about consciousness as a point in a higher dimensional configuration space and try and reconcile that with apparently objective states of neurons, for example, depolarization and polarization?
So I don't want to say that it's a point, the wave function is a point in configuration space. So it's a field on configuration space. Because if it was a point, then that would, that would imply that every particle has a determinate position,
okay,
and that would be
we'll use field rather than point.
Yeah. So I have no objection, to starting from a different place. I'm just starting from a place where in this picture that we're just dealing with the kind of entities of physics, and physics doesn't talk about consciousness explicitly, so that's where I'm starting. The idea of understanding the whole wave function as a field of consciousness, is that the idea, or?
It's just basically mapping your argument onto the brain rather than onto the universe, really. It was what I was thinking, where instead of you talking about a sort of trying to represent a wave function of the universe as your field in configuration space, why not just have, say, the state of the whole brain as your field in configuration space, and then try and reconcile that with a much smaller, apparently objective thing like a state of an individual neuron?
Yeah, right. So that's fine as well. So the argument here, I presented one argument in more detail and then one really quickly. So if there's a reason to think that you're not going to be able to capture the facts about brain states just from a kind of three-dimensional representation, then that would, in the way that the entanglement suggests that you cannot capture the facts about quantum states completely in a three-dimensional representation, yeah, then that would justify a move to represent even that smaller system in terms of a configuration space representation. The other argument about non-locality, I don't think necessarily we have motivation for that, but in this other kind of case, but in general, you know, quantum entanglement, we've known for a long time, gives us reason to think that there's going to be in a three-dimensional representation, some kind of non-locality or action at a distance. That was the other argument.
Thanks.
Thanks.
This is a question for Kevin. Very simple. Are you aware that there is a model, specific model, that directly links very precisely how Tononi's integrated information causes wave function collapse directly?
Can you elaborate? What's the model?
Yes, it's a self-organized criticality, and the criticality involves a perfectly self-observing system. As you get the self-observing system to be in the biological system, which is quite simple, then the self-observation collapses the wave function, but it also generates very high-length coherence, and this creates a state of integrated information. I'll tell you about it later.
Okay, thank you.
I have a two-part question for Kelvin. One, is the M property a refined, specific, and elegant example of property dualism? And secondly, does that not mean that there is no solution to the hard problem that does not include a fundamentally dualist perspective?
So I think I missed something just from the first part, but it sounded like what you were saying was, can we only solve the hard problem in this model if we go the dualist interpretation? Was that the question?
Is the addition of the M property to the physical nature, is that not, in some root sense, a property dualism? You have now created a new property, okay, and that property is in some of its some manifestation, in some complexity, in some as yet unresolved way, fundamentally a new property, fundamentally a dualist property.
So in the general framework of M property theory, we're just defining M properties as some precisely defined property that refuses collapse and responds with refuses superposition and responds with collapse. Now that could be anything, and I gave a bunch of examples of what it could be. One of the examples was space-time curvature in the Penrose model, and that wouldn't lead you to a property dualist view. The other alternative I looked at was phi, Tononi's phi. Now I don't think that's a property dualist view, I think that's still a physicalist view, although the M property is now a much higher level than at the level of space-time curvature. I think I only went into a property dualist framework when I said that the M property was consciousness, such that consciousness is metaphysically distinct from the physical correlates of consciousness. Only then do I think we have a dualist kind of framework.
Quite fair enough, but nonetheless you created the M property in order to deal with the question of measurement of the intrusion of consciousness. And doesn't that seem like that there is at least that connection there, even before you got to the second part?
So I think not quite, and the reason for that is the fundamental goal of M property theory was to develop an interpretation of quantum mechanics that stays as close as possible to the von Neumann interpretation. And when we look to the von Neumann interpretation, we've got this notion of measurement in the formulation. Now, I don't know if that immediately commits us to a property dualist view, but the idea was we just take this notion of measurement and try and make it precise. And I think that doesn't, from the start, commit us to a property dualist theory because of how open we are as to how we are to make that notion precise in the theory.
Okay, I think we have time for one more question, if it's brief.
Yeah, I have a question for Kelvin. Actually, I have an issue with, general issue with collapse and superpositions and measurements and consciousness, and I will tell you why. The reason why we are here is that there were some supernova explosions billions and billions years ago, and in these supernova explosions some radioactive nuclei have been created, systems in superposition which collapsed long time ago. So they collapsed, the superpositions collapsed long before conscious beings were created because measurement devices were created. So isn't this a proof that there must be a deeper reason for collapse of superpositions in nature than just we humans?
So I was using as the theory for the physical correlates of consciousness integrated information theory, and that theory does not tie consciousness to human beings. So if I understood the complaint.
Then you would assume that there is something else but physical entities in the universe, so consciousness, for example, or information, which then would cause a collapse of superpositions after supernova explosions billions of years ago. Is this right?
Well, yes. So on one version of the way that I flesh this out, the idea says the probability per unit time for a collapse is a function of the amount of integrated information of a system. So in the evolution of the universe, we at some point get a certain amount of integrated information in a given system, and that starts to raise the probability that there will be a collapse, and eventually there will be a large collapse. Now, I don't want to speculate regarding the cosmology of that or how early in the universe that actually happened, but...
It must have been at the beginning, right away, because it happens, superposition collapsed immediately after the Big Bang. So in the Big Bang, this has to be then created as well.
Sorry, can you repeat that last part?
Yeah, superpositions were created immediately after the Big Bang, and they collapsed. So everything else that could cause a collapse must have been created then in the Big Bang as well. Otherwise, it couldn't have caused the collapse of the superpositions.
Sorry, just one sentence question.
Let's finish this up at another time. So this concludes the morning plenary. The conference will resume in a half hour at 11:10 with evolution and consciousness. Let's thank the speakers again, Henry Stapp, Alyssa Ney.